All right, great. Thank you very much. All right. My name is Marin Anderson. I'm a postdoc at JPL, and I'll be talking about radio emission as probes of both stellar activity, particularly space weather events, and also exoplanet magnetic fields. So we've been hearing a lot about trying to understand the role of magnetic fields and atmospheric loss. We heard from Ruth earlier today about ways of probing loss mechanisms for exoplanets. And I'm going to talk about sort of the other side of that picture, which is trying to measure exoplanet magnetic field strengths. And it turns out the answer to how to do that, we heard the answer to that earlier in James' very interesting talk, and it's through radio observations. On the other side of that picture, we can also use radio observations to probe the high energy particle environment provided by each of those exoplanets' host stars. And so in this nice artist conception here, what we're seeing is both radio observations of exoplanetary aurora can provide constraints on magnetic field strengths, and radio observations of stellar space weather events, things like CMEs and SEPs, can help us understand the high energy particle environments around each of those planetary magnetospheres. And I'll talk a little bit about, I'll do a lightning tour of developments that have been made recently in this field. And I'll talk about at the end sort of bigger picture, longer term measurements of exoplanetary magnetic fields. If we can start detecting these magnetic fields routinely, forming a much larger sample size than what we have in our own solar system in order to understand the interplay between stellar magnetic activity, atmospheric loss, and planetary magnetic field strengths. So starting with what we know from our own solar system, we know that solar radio bursts can trace the space weather environment. So what we're talking about here is plasma emission produced from bulk plasma motion. And so what I'm showing here on the right is a dynamic spectrum of a solar radio burst accompanied by an X-ray flare observation. So here on the bottom, that goes X-ray flux from an X-ray flare shown by this dashed line, and the corresponding dynamic spectrum from the radio observations. And now the plasma emission is directly related to the density through which the shock is propagating. And what we see is we get these types of bursts called type 2 radio bursts, where we're seeing electrons accelerated at the coronal mass ejection shock front. And the sweep of these bursts is essentially tracing the speed of the shock as it propagates out into the corona. There's also type 3 radio bursts, which sweep much faster than the type 2 radio bursts. And these are associated with tens of keV electron beams that are accelerated at flare reconnection sites or at these CME shock fronts. Now on the planetary radio emission side, we know that all of the magnetized bodies in our solar system produce radio emission associated with precipitating electrons that produce electron cyclotron maser emission. And the frequency of this emission is the electron gyro frequency, which is directly related to the magnetic field strength of the planet. So the frequency at which you can detect this emission is directly related to the magnetic field strength where the emission is being locally produced. And that's what I'm showing here on this plot on the right, which is, if you're a radio planet or exoplanet person, a very famous plot by Philippe Zarka, showing the flux density you can get from this auroral radio emission as a function of frequency. What we see is that we are observing very high brightness temperatures. This emission is as much as 100% circularly polarized. And what we see for most of the magnetized bodies in our solar system is that this emission occurs below about 10 megahertz, which is below the plasma frequency of Earth's ionosphere. So not observable from the surface of the Earth. We need to go into space. But Jupiter over here produces this electron cyclotron maser emission up to frequencies as high as about 40 megahertz. And that's a function of its much stronger magnetic field. So it can produce emission as high as 40 megahertz, corresponding to essentially the surface magnetic field strength of Jupiter. And we can think about scaling up Jovian emission by a few orders of magnitude, sticking Jupiter out at 10 parsecs, and scaling up its auroral emission up by 3 to 5 orders of magnitude, and start thinking about detectability of exoplanets similar to Jupiter. So now stepping out from our solar system, we can think about this as a paradigm of exploring exoplanetary magnetic fields by measuring their electron cyclotron maser emission, and then also probing the stellar high energy particle environment by attempting to measure type 2 or type 3 radio bursts from other stars as a direct probe of coronal mass ejections and things like stellar energetic particle events. So moving on from our solar system paradigm, I'll quickly go through recent developments in this field and remaining questions. I'll also discuss the method we've been using to sort of open up this field of extrasolar space weather monitoring with the Owens Valley Radio Observatory Long Wavelength Array, which is a low frequency radio telescope. And I'll briefly mention the future of this field in terms of space-based arrays. So people have been looking for signs of exoplanetary radio emission through this mechanism I've just described for longer than we've known there have been exoplanets. So this is one of the first papers I could find looking for this type of electron cyclotron maser emission from nearby planets. That was a paper from 1986. And I highlight from their abstract that they state, although the visible and even infrared radiation from substellar and infrared companions is much weaker than that of the parent stars, the radio emission need not be. And indeed, that is the case in our own solar system, where Jovian radio bursts can be brighter than the sun at radio frequencies. So what are some more recent results in this field? Well, there have been detections of pulsed radio emission on substellar objects at gigahertz frequencies. So what I'm showing here is a nice movie showing VLA observations of an M8.5 dwarf. And what we're seeing is pulsed emission. This source is going in and out. And what we're observing is essentially this auroral radio emission as the beam of emission pulses across our line of sight. The detection of this emission at gigahertz frequencies indicates kilogauss magnetic field strengths. And what I'm showing here is the same object, the same observation. On the bottom here is Balmer line emission that's showing periodicity at the rotation rate of the object of about 2.84 hours. And on the top is the radiodynamic spectrum at gigahertz frequencies, going from about 4 to 8 gigahertz, showing that same periodicity of 2.84 hours. So this was a really exciting result. It was the detection of this large-scale auroral current system. So unlike what we would see on the sun, where magnetic activity is driven by small-scale effects lower in the atmosphere of the star, what we're seeing is something that's much more like what we see on the planetary bodies in our own solar system, something much more like Jupiter, where you have a large-scale current system producing this auroral radio emission. The dissipated power in this system was about 4 orders of magnitude higher than what we see on Jupiter. So this detection was really an indicator that we may be able to detect magnetospheres of other objects routinely through this mechanism, and that they may be orders of magnitude brighter than the powers that we expect based on our own solar system. So the prospects for detection are quite good. Another quite recent detection, getting more towards the planetary mass side of things, was the detection of a similar pulsed radio emission, or similar radio emission mechanism, we think, at the location of the hot Jupiter Tau Boo. And this was a detection by LOFAR between about 20 and 25 megahertz, which indicates of order 10 Gauss magnetic field strengths. So potentially very exciting first detection of radio emission and therefore the detection of a magnetosphere around another planet, but a detection that needs to be verified. And we can place on this scale from going from lower mass to higher mass, all of the detections of either auroral radio emission or possible indicators of space weather events. And what we see is pretty good coverage in terms of frequency and therefore magnetic field space. So here's that detection of that hot Jupiter I just showed at megahertz frequencies indicating Gauss magnetic field strengths, detections of kilogauss magnetic fields on ultra-cool dwarfs and brown dwarfs, as well as detection of a similar mechanism, large-scale auroral current systems on active flare stars in the gigahertz regime, indicating kilogauss magnetic field strengths. There's also been a potential detection of coherent emission similar to what we see on the sun. So now not large-scale auroral current systems, but something that looks more like type 4 solar radio emission. So a potential indicator of the ability to detect space weather-like events around other stars. And this was a detection of radio emission from Proxima Centauri.
2 minutes.
Thanks. So going back to this picture of being able to trace stellar CMEs and SEPs and also exoplanetary magnetospheres, I'll say that flares are routinely observed from other stars. across a wide range of field strengths, topologies, spectral types, and ages. But it's still an open question as to how this translates to space weather events in terms of coronal mass ejections and SEPs. CMEs have not been definitively detected around another star. There's been a detection of, for example, blue shifted X-ray spectral lines. But in order to start routinely detecting CME type events, we really need something like radio observations trying to detect these type 2 radio bursts to definitively understand how stars produce, or whether stars produce CMEs across a range of spectral types and magnetic activity levels. For instance, M dwarfs, which can be very active in terms of flaring activity, may not necessarily produce CMEs at the rate we would expect if we're just extrapolating the solar case. So one way that we're trying to measure all of these signposts of space weather and exoplanetary magnetospheres is through the Owens Valley Radio Observatory Long Wavelength Array, which is one of a new generation of low frequency dipole arrays. This array is located in Owens Valley, California, and is currently in its final stage of development. So this is an example of the kind of data product that we can get from the array. This is an image of the entire viewable hemisphere above the array. The snapshot sensitivity we expect with the full array is on order of 50 millijanskis per 10-second snapshot. For reference, that tau boob detection I showed of the hot Jupiter was with the emission was detected at nearly 500 millijanskis. So this is an extremely sensitive telescope to this type of emission that I'm describing. Our strategy is to, rather than target single objects at a time, is to monitor nearly every stellar system out to about 25 parsecs. And the power of doing all of this simultaneous monitoring is that we're sensitive to, in addition to detecting emission from all types of objects, all types of exoplanets, a range of host stars, we're also sensitive to rare CME-driven events, for example, that can increase the radio output power by orders of magnitude. So I'm showing here an example of this with Earth, where Earth's auroral emission increases by orders of magnitude for only a factor of 2 increase in the solar wind speed. So this is just sort of a nice movie to demonstrate our observing strategy. This is a movie showing the full viewable hemisphere above the array. The sky is rotating, and I've highlighted a set of active flare stars that we're monitoring, but I also want to highlight our ability to simultaneously monitor every system out to about 25 parsecs. So looking at the ultra cool dwarfs and brown dwarfs, as well as every M dwarf and all FGK stars, to look for both stellar radio emission and exoplanetary radio emission. So this corresponds to continuous monitoring of about 4,000 systems. So what are the future of radio observations? I put up this map again of our scale of detections ranging from planetary mass bodies up to stellar mass bodies. But what about things that are like Earth? What about terrestrial magnetospheres, where we expect sub-Gauss-ish magnetic field strengths, which requires sub-megahertz observing frequencies? And the answer is space. We have to go to space to get above the limit set by the ionosphere. In the near future, the first demonstration of space VLBI will be the Sunrise experiment, which will be observing the sun, looking for just the type of radio bursts I described, but coming from the sun rather than from other stars. And then further afield, missions like FarSide, which is a proposed probe class mission to put a radio telescope, much like the OVRO LWA, but on the far side of the moon. And the benefit of this, of course, is that we can observe, instead of hundreds of megahertz or tens of megahertz frequencies, we can observe hundreds of kilohertz frequencies and be able to access terrestrial type magnetospheres. And I'll end on this slide and demonstrate the sort of sensitivity that a telescope like FarSide would have to terrestrial magnetospheres. So what I'm showing here on the left is Earth's AKR, 50%, 10%, and 1% of the time as a function of frequency, where you can see that the range here is orders of magnitude. And on the right is what we think we'll be able to detect with something like FarSide. Where I'm showing here is a sample of exoplanets and their expected output auroral radio power as a function of their median flux density, so normal quiescent conditions, as well as those rare events where we would see potentially coronal mass-driven auroral radio emission. And we can see we have quite a good sample of of planets with which to probe for auroral radio emission as a way of directly measuring magnetic field strengths. I'll stop there.
Thank you, Maureen. Sorry, we only have time for one quick question. There's one from chat. How do we know that the radio observations are actually aurora emissions and thus immediately detect the associated field?
Yeah, that's a great question. There's certain properties of the emission that we can look for to be able to say that we think we're actually detecting auroral emission. So things like high brightness temperatures, things like high circular polarization fraction, things like the time scale of the emission, if it's periodic on what we expect to be the rotation period of the planet, and also if we observe something like the cutoff in emission frequency associated with detecting that maximum magnetic field strength from which we can expect auroral radio emission.